Okay. Chemistry, this is for module 13. You see in my little window here, this is what we're working with. This is a worksheet that I made up. For the module, we're going to go through it. So this delta H is, it means enthalpy. And more precisely, it means change in enthalpy. Oops. There we go. So a positive enthalpy means it's endothermic. Just going to cruise through. So we're going to write a balanced equation for the following reaction. We're on number 3 here. So we're going to have complete combustion of CH4. And in order to have complete combustion, we have to add it to oxygen, but not just oxygen. Oxygen is a homonuclear diatom, so it always travels in pairs. And it always makes in complete combustion the same thing, CO2 and H2O. Let's make these look like they're supposed to look here. The next step is balancing this equation. So C's are already balanced. That's easy. The next thing I'm going to do is H's, and there's 4 H's on the left and 2 on the right. So I'm going to give this a 2, make it nice and bold so you can see it. Now that gives me 2 oxygens from carbon dioxide and 2 oxygens from water. So I also need a 2 right there. We are now balanced. Okay, so what we do from this point is look for the enthalpy, this delta H. And what we're going to use is one of the tables from the book. This one, bond energies, okay? So the first section you're looking at is CH. So this is CH right here. Oops, I don't really want to do that. I'm not sure how that worked out. So CH has a bond energy of 411. So underneath this one, we're going to write 411. But there are 4 bonds of carbon to hydrogen. Let me see if I can show you this better. Okay, so I drew our methane molecule right here. Here's our carbon, and it has a single bond to each hydrogen. And what we're measuring specifically is these bond energies right here. So that 411 is the bond right there to break it or to build it. And that is what was 411. Whoops, there we go. So there's going to be 4 of those. And the next one, oxygen. Oxygen has 6 valent electrons, which we could go back to the periodic table. So it wants 8, and it gets a double bond to get all 8, because then it has 1, 2, 3, 4, 5, 6, 7, 8. So now they're happy. So we're going to look at our table for what it is, the double bond for oxygen. So we're back to the bond energies. So this is our carbon to hydrogen. So there was 4 411s. And then oxygen is right here with a double bond. So the value of that is 494. So we're going to go back to our worksheet, and we're going to multiply this by 4, because that's how many of them there are. And then we're going to add it to 494. There is 1 bond of oxygen between the 2 of them, but we doubled the whole thing because we have 2 double bonds. So we're going to put a 2 there. Okay, so now what's next is we look at the carbon and oxygen bond. Now CO2, we're going to go back to our whiteboard here so that we can see how carbon and oxygen go together. So we're going to have our carbon, which has 4 valent electrons like this. Okay, and it's going to connect to oxygen that has 6. Okay, 4, 5, and 6, and we're going to do that again. This is a little more tedious than I thought. Oh, sorry, my O's are horrible. There we go. There's all of our oxygens. Now, carbon wants 8. So if it shares 1, right now it has 1, 2, 3, 4, 5. Not enough. So we share again, now it has 6. And then if we share this side 7 and this side 8. So what it would look like is carbon is going to be double bonded with our oxygen. And it actually is linear. It's not, because there's no other valent electrons pushing it. So it's a double bond. So when we go to this whiteboard, we need to, hello there, trying to find my share button. We go here to our bonds. It is a carbon to oxygen double bond. It's this 799. Okay, so let's go to our worksheet and we're going to plug that in, 799. And how many of those bonds are there? Well, there's 2 oxygens and 1 carbon, which means we have to do this at least twice. And then we're going to add our hydrogen to oxygen bonds. How do I keep losing that? There we go. Our hydrogen to oxygen. Now they can only do a single bond, so there's no wonder if it's a double or not. And that is 459. You can see it right over here. 459. I don't know why that keeps coming up. Hopefully you can see this clearly. 459, let's write that down. 459. Now we wonder how many are there? Well, within hydrogen and water, we've got 2 hydrogens already, and then we're doubling it. So now we have 2 times 2, which is a 4. So we're going to put that in front. Now we just do the math on this thing. 411. This ends up being 2632. And this side ends up being 3434. Oh dear, let's not have them together. But what we need to do is subtract our product from our reactant, and our answer is a negative 802, and the unit on that is kilojoules. So that's our answer. But because it's negative, we know it's exothermic. Energy's coming out. And the way we can see this with math is the energy with our bonds was 2,632, but the energy with our reactants was 434. More energy came out. And because more energy is coming out, we feel that energy in heat. Okay, so let's go to the next one. So this is our answer. We can put that right there. All right, so it says to use table 13.1 for the next question and to draw bonds for each structure. Now this nitrogen, we need to figure out what kind of a bond it is, because here we have C to N. Nope, we need N to N. The only N to N on the whole board is a triple bond. That's a pretty good hint that that's exactly what kind of bond we're dealing with. So I'm going to write 942 and not go through all the steps on that one because there's only one nitrogen option. As you see, this is already balanced for us. See the little 2? All right, the next one is a hydrogen. So let's go look at our hydrogen to hydrogen. Again, there's only one option. It's 432. I don't know why it keeps doing that. Okay, 432. And how many of them are there? So we get 1 bond for each pair, and there's 3 of those. So we have a total of 3. So we are going to put parentheses around this thing and make it a 3. Now the other side is an N to H. We go back to our table. N to H, again, there's only one option. It's this guy, 386. There's probably a better way to do this, you guys. N to H, 386. I'm just going to cancel that. I don't know what to do. Oh, dear. And N to H was 386. My goodness, my brain. 386. Now, how many? That gets to be the biggest problem. So our N to H, I'm going to actually pull up our whiteboard so you can see this. All right, we're going to have our N right here in the middle, and it's going to bond to our H, and it's going to bond to our H, and it's going to bond to our H. Now, nitrogen has 5 valent electrons, so it has actually 2 valence up here, which don't matter for our bonding. But what we see is we have, let's just highlight this thing, is we have 1, to 3 bonds. But we have, let's go back to it for me real quick. We have 2 of them. We have 2 sets of 3 bonds, which means we have 6 of these things. That's a lot of bonds. And in the equation, we take the reactants and we subtract it from our products to get our answer. So we end up with a negative 78 kilojoules, capital J. And because it's negative, again, that means we are exothermic, and this would feel warm in our hands. All right, let's keep going. Hess's law. Hess's law states that enthalpy is a state function and is independent of path. Okay, this delta HF primarily, so that delta H is your enthalpy, and that is enthalpies, oh, I spelled enthalpy wrong, so that's wonderful, is enthalpy of formation. So it's the enthalpy of a formation reaction, which is when you have all the little parts and they make the big parts. So you have your H plus your C plus your O, and they come together and they make a glucose. All right, let's keep going. I made these, I didn't make these little. Next time, be ready. Okay, so here we have a very special word. This is standard conditions. Now, standard conditions means we are going to deal with a different table for some of our combustion facts. But let's first write the equation for a combustion reaction, complete combustion, because incomplete is different. So the first thing is we have our O2. You know what? I can just cheat. I can come up here, copy this whole thing, and stick it in, because I'm going to make the same thing. I might not be balanced the same, so just heads up for that. The first thing I realize is I have 2 C's here, so I'm going to have to put my 2 C's here. And then I have 6 H's, so I'm going to have to turn this into 6 H's by making it a 3. Now I'm just going to count all my oxygens. All right, on this side, I have 2 times 2 is 4, plus 3 is 7. On this side, I have 1, so I need 6 more. This is a 2, and that gives me a 3. We are now balanced. Now what we're going to look for is the delta H degrees. This is the powers, the energy bonds, okay? But because we are in this standard condition, we get to use this. Okay, now the only one of these in here that we have water in a gaseous state. So if you burn something, your water is going to be in a gaseous state. It's not going to come out as liquid, and we have that in our complete combustion. You could add that in here by saying this is indeed in gas, and our carbon dioxide is in gas. I'm just going to do it that way so I don't have to make it big. This here is also in gas, but this would be a solid. We're not burning a gaseous state here. Okay, so now we go back to our standard conditions. In our standard conditions, water is a negative 242. So we can just put that in. Water is a negative 242. And there's 3 of them, so we're going to just put the parentheses around those right now and multiply it by 3. Carbon dioxide right here in a gaseous state, negative 394. Negative 394. And we have how many of those? We have 2 of them. Oop. Okay. The next thing, oxygen, O2. So what's nice is oxygen in our standard formation is a 0. We have a 0 for oxygen. Now it's not on, we actually have 3 zeros if you want to be correct. You see how there's no oxygen even on here, part of what this standard enthalpies is that oxygen is indeed a 0, and that's in your book explaining that one. Let's keep going. All right, so then we have our C2H6O. Let's just see if it's in there. C2H6O in a liquid state. Maybe that's what we have. I bet that's what it is. I put solid, you guys, but I'm wrong. Negative 278. So we can just put that in here. Let's change that. Step 1. Down here is negative 278. And then because all of the negatives were already made for us, we can just, we still need to subtract, all of our reactants from our products. So all of this has to still be separate, even though they are indeed added together. Okay, so that gives us a total of negative 1236 kilojoules. So you have your negative 278, and then you end up subtracting this number, and you end up with a negative 236. 1236. All right. All right, number 8 says to draw an energy diagram that would represent an exothermic reaction and label the activation energy and the delta H reactants and products. So what an exothermic is going to do is it's going to start at a high energy. It's going to go up, and then it's going to come down. Oops, it's not going to have a squiggle at the bottom. And the main thing here is, so this part, hold on. So this section right here would be the reactants, and then the products is just going to be on the other side. And the delta H is going to be the difference between them. So we would just have to really, if we had the numbers on here, which I don't, we'd measure from here to here, whatever that distance is, and that would be our delta H. So if this is at 100, right here, if that's at 100, oops. And then this is down here at 25, our delta H would be a negative 75 because it is indeed exothermic, so it would be negative. Okay, number 9. What is the second law of thermodynamics? This is actually one of my favorites because it shows the evidence of creation. So the entropy, now this is different than enthalpy. Enthalpy is the change in energy. This entropy of the universe must always either increase or remain the same. It can never decrease. Okay, so what entropy is disorder, it's chaos, it's messiness, it is not organization. It's the opposite of that. So what it's saying is that the universe has to continue to get more and more disordered, more and more crazy, more and more chaotic, unless there is energy being put into it. Okay, and so this delta S is the change in entropy, which is measured in joules per moles Kelvin. Oops. I just don't like when the line goes below. Oop, what's going on with that one? So this entropy, this chaos, has to continue, and it gets worse and worse and worse. But it stands in stark contrast to evolution. Evolution says that we keep getting more and more organized. We started as simple organisms, and we became more complex organisms, and more and more and more. And now we are functioning humanity with high levels of technology and systems that are integrated and communications that are integrated. That's order. That's not chaos. And so the law of thermodynamics, which means it's proven, and it's been proven over generations of data, stands in direct contrast to the theory of evolution, and yet they are still both there and they are still both existent, which as a science teacher, I just find that fascinating because they oppose each other. Anyway, get back to it. Number 11, the entropy, so the chaos of a system increases with increasing temperature. What that primarily means is the more temperature you add, the more crazy things are going. They're just moving around everywhere. All right, what is the sign for the delta S in the following equation? So what we're going to use for this is we're looking at the gas molecules on the reactant side and the gas molecules on the product side. So there are 4 gas molecules on this product side. We've got 1 in nitrogen and 3 hydrogens for a total of 4. And on the product side, we have NH3, which is ammonia, and we only have 2 of those. These are not counting bonds. These are actual molecules because it's the molecules that bounce around. It's the molecules that are moving. So on this side, we just have 2 gas molecules. Therefore, our delta S, let's see, let's just use this guy here. Our delta S is negative. It is greater in one side than it is in the other. Okay, next one. We're going to use table 13.3 and we're going to actually calculate this delta S for our CaO, our carbon dioxide, and our calcium carbonate. And let's plug this in. So we're going to use table 13.3. Let's go grab it. There it is. So the first one is our CaO, and it's in a solid state. So that's this one right here, a 38.2. So let's write that down. Oh, guys, I don't know what's happening here. 38.2, 38.2. And then we go back and we're going to get our carbon dioxide. Carbon dioxide right here is 214. You see where I'm at? So we've got a 214. Oops. And then we have to go get our CaCO2. CO3, I'm sorry. Calcium carbonate right here at 92.9. Let's type that in. That's going to go underneath this one. 92.9. All right, so now what we're going to do is we're going to subtract. This is the opposite of enthalpy. Enthalpy is products subtract reactants. I'm sorry, reactants subtract products. This one is products subtract reactants. So we're going to take our 92.9 and we're going to subtract our 38.2 plus our 214. Oops. And this is going to have to be in parentheses, otherwise it's going to get all messed up if you're putting it in your calculator. And this is going to give us a negative 159 joules per moles Kelvin. That's all we're looking for, is just, can you use a table in an equation and find an answer? Okay, so here's our next delta letter. We have our delta G, and G is our Gibbs free energy. Oops, if we can spell energy right, Gibbs free energy. And it is used in the equation of, this is what puts kind of all of them together. We have our delta G is equal to, we're going to use all of these here. And we're going to also go get our delta H somewhere. Here we go. Just bringing them all together. Probably could have had this set up for us. So our delta G is equal to our delta H subtract our temperature times our delta S. So our Gibbs free energy is equal to our enthalpy subtract temperature times entropy. So if temperature goes up, entropy goes up. Temperature goes up, chaos goes up. Enthalpy is our bond energies, and our bond energies subtract our chaos gives us our Gibbs free energy. And when our Gibbs free energy, go to 15, is less than 0, the reaction is spontaneous. It's just gonna happen, just boom. So that means when it's negative, when our entropy, our chaos, is going to be greater than our bond energy, our reaction is spontaneous and just happens. All right, so we're going to use our last table, 13.4, and we're going to find our Gibbs free energy for this equation. All right, here we go. Let's go get it. Here's our 13.4. Standard Gibbs free energy. This is our kilojoules per mole. And the first one is our calcium. Now, calcium has no set bonds. It is an all by itself solid, free-floating thing. So as you see, there is no calcium here in our chart, but it is a free element, so it is a 0. Now let's go get our HCl, our hydrochloric acid. Here it is in an aqueous state, which is us, and it's a -131. So we're going to get that next. So we're going to add, there's 2 of these, and we're going to put it in -131. All right, now we're looking for our calcium chloride. Calcium chloride, here it is. Our calcium chloride is a -750. We're just using our chart, okay? And that is a -750. There's only one of them, so we don't need to multiply it. Now, here's our hydrogen. Again, our hydrogen, it's in a gaseous state. It's to itself, it's just an element. You could double check it. There is no hydrogen in our table. So hydrogen itself also gets a 0. Here we go. So what we do now is very similar to our entropy, we subtract our product, our -750. We're going to subtract from our 2 times -131. And that gives us a number because we're now subtracting a negative, right? Subtracting a negative, we're going to end up with a positive number of 488 kilojoules. Which means it is spontaneous, not all the time, at 298 degrees Kelvin. That's not right. This should be negative. My bad. Because it's -488, which makes it spontaneous. That's where this comes in. And it's spontaneous at this temperature of 298 Kelvin. Okay, that is the end of our Module 13 worksheet. If you have questions, please reach out. Use the tables. The symbols are the dead giveaway. If it says it's in standard form, you're going to use 13.2. If it says bond energies, you're using a 13.1. If it says entropy, which is the delta S of chaos, we're using 13.3. And if Gibbs is mentioned, it's 13.4. This module is a little bit about you understanding the concepts, but a lot of it, honestly, from the outside is, can you use a table and know when which table can be used? That's a skill beyond chemistry.